Okay. All right. So we have considered one operator. When we have more than one operator, so you should think of operators as observables. Operators in quantum mechanics are observables. So what are some examples of observables? Can someone tell me? Because this is not your first quantum class.
So momentum operator.
Position pair.
Good.
Yeah.
So momentum. Anything else?
Hamiltonian.
Hamiltonian. Yeah. Which is also known as energy. Good. Position. Anything else?
Angular momentum.
Angular momentum. Okay. Wajia, what do you think? Can you give me an example?
Sir, it could be any measurable properties.
Yeah, but what would come to your mind? It can be anything from this list.
Energy, kinetic, or potential energy.
Energy. Good. So Wajia said energy. So which Nahi called Hamiltonian. Kamoon, do you have any preference? Earth calling moon?
There is this time evolution operator.
That's good, yeah. But the time evolution operator is not an observable. It is related to the, as we shall see, the Hamiltonian observable, but itself is not an observable. It's not an operator. It is an operator, you're right, but it is not a Hermitian operator. So you're very right. So I should write Hermitian operators here.
Okay.
I'm going to add one more, which I like, is spin, which is of course covered in angular momentum, but angular momentum can be two types, spin and orbital.
So, sir, the proper definition of observables are they should be Hermitian operators.
Exactly, yeah. Yeah, very good. Okay, so suppose that we have more than one observable, say A and B. Now, in classical physics, when we multiply, say, momentum and say position, it doesn't matter what order we multiply them in. Or physically, if we observe the momentum and the position of a particle, it doesn't matter what order we observe them in. But in quantum mechanics, they do. And that is reflected in the fact that in quantum mechanics, some of these operators do not commute. So this is, in quantum mechanics in general, operators do not commute. So in general, operators do not commute. Okay? So when operators do not commute, there's something interesting that happens. So what we've talked about so far is the eigenvalues of the operators. So suppose we have A as an operator, and it has some eigenvalue spectrum. Okay, so this is the eigenvalue spectrum, and suppose that how should I do this? Yeah, so you have some number, and here is the expectation value of A. So if I now plot this, the plot would be some kind of, plot like this, right? Sorry, what I mean is the following. This is not what I mean. What I mean is, suppose that you have some A eigenvalue. This is the possible eigenvalue along the x-axis, and along the y-axis, you have the probability of the of that value occurring, right? Now, if I ask you what the average A is going to be, what this thing is going to be, you're going to say that, you're going to guess, right? You're going to say, oh, it's going to be somewhere here, right? Because most of the probable eigenvalues are here. So the average, and these are going to cancel out the, these guys. So the average is going to be somewhere here. So that's correct, but the average is just one number, right? The average is the first moment in the language of statistics. To characterize the eigenvalue spectrum of an operator, we should use also how far the eigenvalues spread, right? And for that, the second moment is very useful. The second moment is something like a squared, but but that's actually not this spread. This spread is known as the standard deviation, delta A. And the standard deviation is defined to be, it's easier to define the square. It's defined to be A, the operator, minus its average squared, and then the average of these deviation, that is the standard deviation squared. Okay. Now, if I expand this, what do I get? I get A squared minus 2A A plus, this whole thing, taking the average. Okay, but the average and the average is linear, so I can write this as the average of A squared minus 2 times the average of A times the average of A plus the average of A squared. But this is just the average of A squared, so I can write this as A squared, average of A squared, minus the average of A squared, right? So in other words, the standard deviation is square root of the average of A squared minus the average of A, then squared. Okay, so this is basically the standard deviation. And what is delta A? Delta A is a measure of the uncertainty of the result of a physical experiment. So what do I mean by that? What I mean is that when you're making an observation on an observable, say A, you have to have your system in some state psi, right? So this is, suppose you're measuring. In some sense, you're measuring the average of A. And how do you do that? You have, say, lots of copies of psi. Right, so you have the identical copies of psi in your laboratory, and you make measurements of A on it, right? But for each measurement, you get some eigenvalues, A1, A2, say A3, A1, A1, blah, blah. So what you see is that you get some average value of A. So if you take the average of these things, you get some average. But there, you're not always getting, so suppose the average value is, say, some, the average value is, sum over pi of A. This is probability times AI, right? Now, the average value doesn't have to be one of these values. What's more is that, so the average value is, even if it was one of these values, it's not the value you're going to get from every experiment. There's going to be some uncertainty. Sometimes you're going to get something less. Sometimes you're going to get something more. So the uncertainty, like how far from the average you expect to get your, say, your observation, that is measured by delta of A, the standard deviation or the uncertainty. Okay, do you understand this?
Sir.
Okay. Now the thing is that what you can do is that you can devise a very, 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 very precise experiment such that you choose a state which is so finely tuned that you are going to minimize delta A. Right? You can measure, you can create a state where you know that if you observe A, it's going to give you exactly the same number again and again and again. So that's how you have prepared your state. That's possible. Now in classical physics, suppose you have a system where you know precisely what the momentum was, then if you measure its momentum and measure its position, the measurement of the momentum is not going to affect the measurement of the position. But in quantum mechanics, it turns out that the position operator, say x hat, and the momentum operator p hat, they do not commute. And as a result, the value of delta x influences the value of delta p and vice versa. But so far, I've been talking in abstract terms. And in abstract terms, if you have two Hermitian operators which do not commute, then the uncertainty in A times, so this is just a number, right? So I can just multiply it with another number. The uncertainty times in A to the uncertainty in B is a positive number, which is greater than or equal to half times the modulus of the expectation value of the commutator of A and B. Okay, so this is a very fundamental result that you will prove in the tutorial. Okay, so I'm not gonna, I have done it in my Quantum 1 class, and you can always look it up, but this is a very important result that you will prove in the tutorial, okay? So now it turns out that for quantum mechanics, the fundamental variables are usually the position and the momentum, and they don't commute. Their commutator I times h bar times the identity operator. So if you use this formula, then you get delta x times delta p that is greater than h bar divided by 2. Okay, so this is a very famous formula. This is known as the Heisenberg uncertainty formula or uncertainty principle. Okay. Okay. So any questions?
No, sir.
Okay. Anyone else? So notice that this formula is also valid for operators that do commute. So for example, the position of the particle in the x direction and the position of the particle in the y direction, and it turns out that in quantum mechanics, they commute. And therefore, delta x times delta y is 0. Or, sorry, it is, yeah. Sorry. Okay. So in principle, so what is the Heisenberg uncertainty principle telling us is that if I make a measurement very precise, so delta x goes to 0, then delta p will go to infinity, right? So the more precisely we measure the position of a particle, the less precise we have information we have about the momentum of that particle, okay? And vice versa. Sorry, I'm gonna sneeze a lot. Okay, any questions?
Sir, does the anti-commutator has anything to do with this thing?
No.
Heisenberg?
No,
Oh, okay.
and the commutator has other applications, but it's not related to this. Yeah.
Oh, okay.
Anti-commutators usually have to do with fermions. Okay, so fermionic operators anti-commute. So Fermi statistics involve anti-commutation.